Okay. All right. So I hope it will record because suddenly it says I don't understand why it says not enough space. Okay. All right. So last time I asked all of you to watch some videos on BJT, right? Bipolar junction transistor. Okay. So I hope you watched. So before that, let's go through the slides because there are, if you look in the folder, there are some slides that I gave and there are some things that I missed. So let's go through that first before we go to BJT. Share screen. So if you look in the slide number 3 in the folder of the slides, I will now open slide 3. Yeah? Okay, can you see my screen? Yes, no, don't know.
Yes, we can see.
Okay, so slide 3 starts with scattering. So I think we talked about scattering before, right? Benar tak? Semua tak ada suara ini kenapa?
Ada.
Ada. So scattering, there are lattice scattering and impurity scattering. Lattice scattering kan hari tu saya kata lattice scattering, that the one I think the one that I talked before is lattice scattering, where it's due to the thermal vibration of the lattice. So remember we have atoms and in a lattice, and if the temperature increases, this lattice will vibrate. Therefore, this lattice will vibrate. Therefore, it will increase the scattering. And it's in the proportion is roughly T to the power of 3/2. Another thing is you have also impurity scattering. Impurity scattering is scattering due to the impurities inside the semiconductor material. For example, so now in this case, dia ada laser. Oh, menarik. Okay, so I just found something interesting. So I have a laser pointer. See, it will go away. Right. So I just bought this software. So I'm very happy. Now I don't have to rub off every time. Okay. So so this is a lattice scattering, right? And on the so this lattice. So when you have impurities, when you have you dope it with acceptor or donor, right? For example, let's choose another color. Purple lah. I hope none of you are colorblind. Anybody colorblind here? Ada ke? Normally, the statistics says normally the colorblind are the brothers, the male. Higher chances of getting colorblind. Very rarely you see women. Women can women can differentiate even tudung sister, betul tak? Turquoise lah, biru, many shades of blue. Allah gifted that to the female. They will see the difference. Normally colorblind ni brothers and and the problem is we have colorblind, you cannot be pilot. If you are colorblind, definitely you cannot go for to take exam to be a pilot. Before the exam you already fail. So because you cannot be colorblind, certain occupation that needs apa nama tu, that needs for you to be able to differentiate colors. Okay, now apalah, tak berapa penting pun. Maybe you can see if you colorblind pun tak apa pun. Okay, so now this is the lattice. So for example, so this is the lattice. Sometimes you have impurities. Kerana dia duduk kat sini, impurities meaning the acceptor atom or the donor atom, right? The purple. Now I'm drawing the purple color here to resemble the impurities. So you can see if the impurities are more, if you increase more impurities, so there will be more vibration of these impurities. So therefore there's impurity scattering. So if you increase the increase the concentration, you want to increase the number of free carriers, therefore you dope it higher. You dope it with higher concentration of acceptor or donor. It's good, it will increase the number of free carriers. However, there's a side effect. And this side effect is the impurity scattering. You will increase the impurity scattering rate. So therefore, when you have scattering, remember what does it affect if the scattering rate is high? It affects what?
Mobility.
Mobility, okay. So it will affect the mobility, hence it will affect what? So what if it's affect the mobility?
Electrical properties.
Yeah. So what's the electrical properties that it will affect?
Conductivity.
The conductivity will affect what? What's ultimately the most important thing?
The current.
Band gap.
No, it will not affect the band gap. It will affect the current, I. Right? Mobility, conductivity. In the end, it boils down to the current. I equals to what? Mobility times something, right? So in the end, all these, to us engineers, the most important is the current. We know the first thing you learn in first year is the current, the Ohm's law, V equals IR, right? So I is important, R is important, V is important. So everything here will affect the current, and therefore will affect the performance of the device, and therefore will affect the performance of the equipment or circuit that you are doing. Okay, so scattering is not good because it will affect the current, the mobility, the conductivity, therefore the current. So if the scattering rate is high, how about the current? Is it high or low?
Low.
Yes, low, right? If scattering is high, then the current is low. So then you want a certain amount of current, then it become less. So it's not good. And it will also increase the heat. Because scattering means it will collide with each other. You know when the electrons travel, it will hit there. So there are many hits. It will slow down and maybe increase the heat, heat dissipation inside the device. Okay. So the main factors influencing resistance of a solid state material are carrier concentration and scattering. Okay, so it means that the resistance that you for the V equals IR, this is the Ohm's law, this resistance here for a semiconductor, what are the parameters that affect most the resistivity or the resistance? Is carrier concentration. If you have less carrier concentration, you have less free carriers, therefore you will increase the resistance and also the scattering. Okay, any question? No? Apa pula tiba ni band gaps of common semiconductor? Okay, this is good just to see, this is a common semiconductor band gap. It's a what do you call it? Convenient graph. So you can see this is the band gap and this is the wavelength. Okay, and the band gap and the wavelength is inversely proportional. So that's why the arrow is here and the arrow is here for EG. So silicon, the band gap is 1.1. So that's why it's here. Okay. And then the, what do you call it? The germanium is slightly like 0.7 over here. So, and then you have in this simple diagram, they divide it into infrared, visible, and ultraviolet region. So this is the visible region here, where you can have a semiconductor that gives out the color of red, yellow, green, blue, and violet. Okay, it depends on what material. For example, if you want red, you can use cadmium selenide. Yellow, maybe between green and yellow, maybe gallium phosphide. Okay, silicon carbide. Silicon carbide is actually not a direct band gap material, so it will not give out light. Although it's what they call it, although the band gap is at this region, this is correct, but it's not, silicon carbide is not a direct band gap material, so it will not give out light. So this is interesting lah. So this, as you know, the color of the light depends on the wavelength, and this wavelength depends on the band gap, therefore depending on the material. So if you want a certain color of a light coming out, you need to check on the band gap, therefore the material that you want to use. Okay, any question, just stop me. Okay, so when we talk about scattering before, the scattering will affect the mobility, and this generally, I'm just telling you what you need to know. If you want to know further, you can read or you can ask me later. So number of scatter center, so the higher the number of impurity and defects, therefore you have more scatter center, therefore the number of scattering rate will increase. So more doping means more impurities, more scatter centers, therefore lower mobility. We mentioned this before, I'm just reiterating. If you have more defects, right? We talked about defects before. The defects will affect what? Who can tell me? The defects inside a semiconductor will affect what characteristics?
The lattice structure.
The lattice structure, yes, it will affect the lattice structure. So for us in the electrical, on the engineering side, so what if we have defects there? Maybe it looks horrible and ugly, but if it doesn't affect anything, performance, why should we care, right? Because it's like the headphone, for example, it's ugly there, no problem. You don't look at the semiconductor. But what's actually is why we are concerned about defect. What does it affecting us? But yes, it's affect the structural property. What else?
Electron traps.
Electron traps, good. So what does the electron traps do?
It traps the electrons, so the electrons can't move.
So what?
So then less current.
Okay, you are saying higher defects, less current. Is that what you're saying?
Yes.
Okay, interesting. So let's have a discussion. Everybody agree ke? Higher defects, less current. Who agree? Who agrees? You only have two choices. Agree or disagree. If you don't have any answer, I will kick you out from this room. Discuss. So, okay, let me ask now. So you need to make up your mind. In life, tak ada atas pagar. We need to know what is right and what is wrong. Okay, who says more defect, less current? Put a reaction. Including yang tadi yang jawab tadi lah. So Anas. Who else? Seorang je. Anas je. Tadi. Tapi siapa yang bercakap tadi? Anas seorang je. Yang tadi jawab tadi Anas Who answered just now? Hello. answered just now? Siapa yang jawab tadi bila saya tanya effect of defects? Tiba-tiba tak ada orang. Do you understand my question? Do you understand my question or no? Mohaimin, do you understand my question?
Yes.
Siapa apa soalan saya?
Soalan medium, just when we have higher defect, we produce less current.
Yes, bukan. Soalan saya pasal siapa yang cakap tadi.
Oh, siapa cakap?
Siapa yang cakap tadi? Who knows? Sila mengaku. I know siapa yang cakap tadi. So you better mengaku. Saja je saya tanya.
Kan saya kan?
Huh? I think
Orang lain kan?
awak yang jawab tadi kan?
Oh, Madam tanya pasal saya ke? Ingatkan orang lain.
Yelah, awak tak faham soalan saya tu. Saya tanya awak faham ke tak soalan saya? I was asking who answered my question just now. Pasal yang effect of what's the effect of defects to the semiconductor? Then you answered, if you increase the defects, you lower down the current, right? Betul tak, Haris?
Maybe dia susah nak regulate the current kot.
What do you mean?
Sebab defect can also be the higher concentration juga. The concentration isn't right kan?
No, my question is simple. If the defect is high, how about the current? Tu je soalan saya. So high or low? Semua orang jawab high or low? Jawablah hati nanti saya tanya, okay?
High, medium, high.
High?
High,
Dia pula
tinggi.
Anas kata low. So why do you say, okay, let's say saya nak tengok siapa kata high, make a reaction. Now. Satu, dua, tiga, empat. 5, 6, 7. Okay, siapa kata low angkat tangan? Who say apa nama ni? Increase the effect, reduce the current. So Anas seorang. Afiq, awak jawab yes ke?
No, I don't know how to cancel the reaction.
Okay, so brothers and sisters, the answer is, I think we go through this before. What happens if you have defects in the band gap?
It will make the electron easier to go to the conduction band.
Yeah, so it has like a stepping stair for it to go. Therefore, you will increase the current. The answer is the current increases. So bagus ke tak the current increases?
No.
Why
Because
not?
Bagus.
Afiq kata bagus.
Ya, bagus ada.
Bagus.
Dia bagus sebenarnya,
but
tapi kita tak boleh nak
defect is
regulate.
unpredictable. Because
Tak boleh predict.
you cannot control the defect, how the lattice form.
So overall bagus ke tak bagus?
Because
No.
No. Okay. Senang kita jawab no je lah kan. So overall it's not good because whenever you cannot control, you don't know what's going to happen. Crazy. Tiba-tiba sekejap komputer. Imagine hari ni you turn on the computer, it works. Tomorrow you turn on the computer, it doesn't work. 20 seconds later, it will work. That's not really like, I mean, people will be, akan ngamuk kat awak lah selling a laptop that you can, the behavior is unpredictable. So the answer is, you increase the defect, therefore you increase the current as well. And here, okay, we going back to my apa nama ni slide tadi. Macam mana ni? Tak tahu kadang dia keluar. Sekejap. This is difficult. Saya ada buat dua skrin ni, dia macam tak tahu nak macam mana. Oh, doesn't want to go away. Macam mana nak buat ni? Sekejap. Let me.
Jangan masuk. Jangan masuk. Lihat. Ambil ni dia. Jangan masuk. Tengah kelas.
Tengah kelas. Tapi tak nak buka skrin ni. Kejap. No, just kidding. Aduh, macam mana ni kedap. Susahnya buat apa. Dia jadi macam stuck. Oh ya Allah. Macam mana kita stop sharing dulu. Stop dulu. Saya cuba restart baliklah saya punya iPad ni. Okay. Sementara tunggu dia on. Let's do some exercise. Okay, while waiting for it on, I want you to get a piece of paper. A small paper pun tak apa. Okay, everybody. Okay, got it? I want you to write down the name of a person that you are grateful for. Okay, and why? So write down the name of the person you are grateful for, and why, and tell why. And you need to tell what's the relation of that person to you. It can be somebody or still alive or dead. Okay, somebody that you are grateful for. Okay, give you 2 minutes to do that.
Is it only one, madam? Or it can be more than one?
Wow, you have more, a lot. Good. So only one.
Okay.
Dia
So
nak teli bini dia tu. Nak teli bini dia tu.
Tulis apa?
Bini.
Dia dah kahwin?
Dah.
Dah, madam.
Alhamdulillah. So you get seorang je lah. Seorang yang paling you are grateful for. So kalau ada 10, 200 ke, seorang. Okay. And then you write down your name there, take a photo, put in the Telegram. If you are done, put in the Telegram. Is it better to put in the Telegram or you PM me? It's up to you. But either way, I need to be able to read it. It's either you put direct in the group or you PM me in the Telegram. But make sure your name is there. And that will be your attendance for today. Dah ke? Tak payah tulis karangan. Dah sikit je. Just a few sentences. because sometimes we forget to be thankful to the people around us or people that we have in our life. Cuba sikit. Dah? Okay, finish. Send. Dah? Belum. Okay, semua dah. Time's up. Time's up. Send it to me. Okay, brothers and sisters, can somebody read this ayah for me? A'udzubillah minasyaitonirrajim. Somebody. Tak mana baca Quran ke?
أعوذ بالله من الشيطان الرجيم ربي أوزعني أن أشكر نعمتك التي أنعمت علي وعلى والدي وأن أعمل صالحا ترضاه وأدخلني برحمتك في عبادك الصالحين.
Okay, thank you, Afika. Which means this actually in the Quran where Nabi Sulaiman, Prophet Sulaiman, make dua to Allah. And it's a beautiful dua that all of us should memorize and use it in our daily life. You say, Rabbi, my Lord, Tuhanku, Auzi'ni, gifted me, enable me, an ashkura, to be grateful. Ni'matakallati, all of your favors, segala nikmat yang Allah berikan, allati an'amta alayya, semua nikmat yang telah engkau berikan padaku. So number one is for us to realize all the favors and nikmat that Allah gives to you. Wa ala walidayya, and also all the nikmat, favors that Allah has given to our parents. Wa an a'mala salihah, and to do righteous of which you approve. Wa an a'mala salihan tardah, and he make dua, ya Allah, gifted me to make amal soleh that will make you redha on me. Wa adkhilni, and masukkanlah aku birahmatika, dengan rahmatmu, fi ibadika salihin, among your righteous servants, hamba-hambamu yang soleh. So even this is the Prophet Sulaiman who already have everything in the world at that time. He can even apa tu kata dia tu, menyuruh jin dan angin. He can give instruction to the jinns, all the jinns, and to the wind. And he asked Allah to gifted him to be to do amal soleh and be among. He doesn't say that he's from the soleh, and to put him with the hamba-hamba yang soleh. Amazing how humble Prophet Sulaiman is. So brothers and sisters, in life we need to be grateful for many things, including people around us. Sometimes we forget to be grateful of many things. We always focus on the things that we don't have. We are stuck in the mahallah. We cannot go outside. We cannot go traveling. There's no holiday. So we are focusing on that rather than all the other blessings that Allah give us. So there are a lot more blessings, including people around you who care about you. So when you have things that you are grateful for, Allah asks us to show, untuk menunjukkan kesyukuran kita. So number one is to be thankful to those around you who you are grateful. So I don't know who you wrote. If it is still alive, you should say thank you to that person. If the person already dead, make a lot of dua to that person. Okay? So that's because sometimes we just forget. There are a lot of people around us that we are grateful for. Okay, saya rasa dah patut boleh masuk dah saya punya ni. Okay, cantik. Alright, so we talk about mobility. So we talk about apa nama ni? The scatter centers. Kenapa dia tak nak menulis pula ni? Okay, and also the the rate of scattering. Oh, patutlah battery slow. Okay, so the rate of scattering will depend on the density or the concentration of the impurities and defects, and will also depends on the temperature. Okay, so the higher the temperature, the more vibration you will have, and the more scattering that will occur. Therefore, it will reduce the mobility inside the semiconductor material. Therefore, will reduce the current. So when you explain in your exam or quizzes, jangan stop tau. Jangan kata oh it's affecting the mobility. Stop. Then maybe you get half the marks. You need to go until the end. So starting from the temperature, go to next. In the end, it has to go to either it should show what happens to the final result. You mean the current. Okay. So whenever you explain in the quiz or the exam, make sure you explain till the end. By the way, I haven't marked the quiz. I've looked roughly. Macam semua orang boleh jawab. Macam betul ke ni? Awak boleh jawab ni, kau buka buku. Tapi kita kena husnuzon. So baguslah kau boleh jawab. Okay. Now, mobility is also a function of electric field. Okay. So when you have, remember mobility, what is mobility? Siapa nak jawab? What is mobility?
How well the particle move due to the electric field.
How well?
The particle move due to the electric field.
Yes. How easy or how well the carrier yang guna particle. It can be dust particle ke apa particle apa tahu. Now the carrier moves inside a semiconductor. And so this mobility, when we say there's a flow of carriers, most probably there will be electric field. Kalau bukan diffusion lah, if it's drift, there will be electric field. So this electric field, so the higher, so you can apply electric field. Remember what's the relationship of electric field and voltage? Ingat tak? Saya ulang banyak kali lah. So electric field is voltage over distance. Whenever you have voltage, whenever you have voltage, you have distance, you have electric field. So mobility is also a function of the electric field strength. Okay, so whether it's big or small. So if you look at this graph, do you understand what this graph is about? Walaupun dia macam squash. Okay, so this is a graph of macam mana tukar lah? Oh, dia boleh tukar. Okay. So the electric field Ex here is electric field, volt per centimeter against the velocity. Velocity of what? Is the velocity of the velocity apa?
Carrier.
Yeah, so the carrier electron or hole inside the structure. So you have a graph here is the electron hole. So you can see the velocity of the hole is always less than the velocity of electron. Why? Because hole is heavier. Dia gemuk sikit. So dia lari tu slow. So jadi so you have electron hole. So they are interesting. Allah make electron hole are pairs. Tapi each one have their own characteristics. Macam kita lah manusia, lelaki perempuan. It's a pair tapi dua-dua lain, tak sama. Dia ada benda yang sama. Dia ada hidung, telinga, mata tapi the characteristic is different. So it shows the beauty and the intricate of Allah, Al-Halim. When Allah created something, is very intricate and very detailed. So, okay, so this is electron and this is hole. Okay, so this is a graph. So as you increase, if you look at the apa nama ni x-axis ni, is as you increase the electric field, the velocity increases. Okay, so it means that you maknanya you ramp up the voltage the more battery letak, patutnya lagi laju carriers will move inside the semiconductor. Therefore, you have higher currents. So you letak more battery, more current macam tu. So because battery means voltage and if you have distance, you have electric field. Now, however, nothing is unlimited in this world. Tipu kalau unlimited. Kalau dia kata data carrier tu apa yang macam mobile apa nama ni? You mobile ke apa dia kata unlimited, ya ke betul unlimited? Sebenarnya when you say unlimited tu, dia limit kat tempat lain, right? Betul ke tak betul?
Betul.
Yes, there's nothing unlimited. So although if let's say all of us use the maximum, they will reduce the speed. So there nothing as such a thing as actually unlimited in this world except for Allah. Hanya Allah yang unlimited. Allah will go beyond. Kita semua akan mati, dunia ni akan hilang, tapi Allah is forever there. So that's why kalau if you look at science everything, there will always be limitation. There will always be limitation. That's why kalau in engineering, we need to design, we need to specify what is the limitation of our design. So you say this laptop, let's say you created a laptop. So there's a limitation of the laptop. Can you use the laptop in a 1000 degrees C environment? Of course, no. It can work, but it can work to a certain. So there's always limitation. Can it work in the space where there's a lot of radiation? Space radiation, maybe not. Oh, like yesterday I had a talk with the US military. US. They have a grant. They have a fund money to fund a project or research, which they think is what they call it, interesting or important. So I submitted. They have this money for space research. Okay, space research. Now I don't know. If you look in the world now, people are crazy on the space. Awak baca tak news? SpaceX, apa nama tu yang shuttle tu kan, Elon Musk. Kau semua ni baca tak news? Right? Go and read the news. This is like people are all, what's the word? Berlumba, racing towards going to the moon. So now later, maybe I don't know, 10, 20 years, it will be common for people to have a holiday at the moon. The rich people lah. So that number one on the holiday. You know why? Ni kita stop recording kejap. Okay. If you think what I said just now is wrong, tell me. Kalau apa yang saya cakap just now is wrong, tell me. We have a discussion. Whether you think, taklah madam, you are wrong. Let's have a discussion. Boleh? Okay. Yang penting jangan kita tenggelam dengan hawa nafsu kita. Yang penting jangan kita tenggelam dengan hawa nafsu kita. Sebab yang ruginya kita, Allah tak akan rugi. Kita yang rugi. Okay, so now this is a graph again of the electric field. Versus the velocity of the carriers, right? So it can be fast. The more you put the battery, the more the higher the electric field, the faster it will be attraction for the carriers to move. So however, you can see in the end, it doesn't go, so you cannot keep on increasing the electric field. Because at a point, you will see the velocity is saturating and with a VSAT, saturated voltage, saturated velocity. So because at one point, if you keep on increasing the voltage, the carriers will move. The carriers, the electron will move throughout the lattice. Dia akan laju kan. As I mentioned before, if it's very fast, because as you increase the electric field, the velocity will increase. If you drive a car and it's very fast, is it easy to control the car? No, right? It's very difficult. Kadang kat Selekoh especially, I sometimes a bit afraid, I need to slow down because corner tu macam, you might hit something. So the same with the carrier. At the very high electric field, right? The velocity is very high, 10⁻⁷ centimeter per second, and difficult to maneuver. Therefore, the velocity becomes saturated. It cannot increase anymore because dia akan hit. They keep on hitting banyak lagi. So and because of the scattering. So at high electric field, scattering increases. Therefore, you get velocity saturation, which means that you cannot get further increase of current. So if you keep on pumping the higher voltage and higher electric field, the current will stay stagnant at a certain value of the electric field. And this is value of the where it starts to saturate is different from one material to another material. Some material will have a higher point, some not. Okay, tapi why you have velocity saturation is because of the scattering. Okay, ada soalan? Ada soalan, brothers, sisters? Senyap pula. Okay, what does it? Yang ni saya skip. Yep. Okay, so we talk about before the generation and recombination before, right? Dah kan? Dah ke belum? Yes, right? What is generation? Oh, ada soalan dalam quiz tu. So we gone through this. So I only talk about direct band to band dengan indirect through research RG centers ni. This RG centers is basically traps. Kadang-kadang it can be the name is defect level, trap level. It can be also RG level or RG recombination generation centers. Dia banyak nama. Okay, it's the same thing. Saya tak cover yang ni. Kalau berminat kita boleh discuss. Sebab dia macam it only occurs at very high. This one it only occurs at very high carrier concentration. Remember we talk about the EK diagram before. Biasa sebelum ni saya lukis je. This is actually the actual graph. This is the wave factor, momentum versus the energy, the band gap, the energy. So you can see here this line here and this line here. So both the conduction and the valence band. So this is the conduction band of a gallium arsenide and this is the valence band. Madam, apa lagi yang banyak-banyak ni? Okay, it's complicated. The band gap actually have many values. When they do research, they find out, bukannya satu je conduction band yang banyak-banyak. Tu complicated, tu PhD level lah. Okay, so for your information, this is the lowest of the conduction band kat sini, and the highest of the valence band kat sini. And if the minimum of the conduction band meet the maximum of the valence band directly, therefore this is a direct band gap material. Okay, so just showing you the actual graph. Kalau buat eksperimen dia dapat graph ni lah. Okay. And this is example for direct band gap material. This is gallium arsenide. This is the example for silicon indirect band gap semiconductor. So you can see this is the lowest of the conduction band. And the maximum of the valence band. And you can see the minimum or the lowest of the conduction band is not exactly the same as the maximum of the valence band. So that's why it will change momentum. Ni EK diagram. This is the momentum. So whenever recombination happen, it will need to change momentum. Therefore, we will not give out light. No photon. Ionization I just explained before. Dia sama je. So basically benda sama je. So saya kata don't trust everything. Kadang saya repeat, kadang tak apa-apa saya letak dalam slide ke saya. Just to make sure you come to the class lah. Can you imagine you just read the slide? Memang tak pas aku. So mungkin awak pas. Kalau genius awak boleh pas. Awak baca, awak khatamkan satu buku yang saya bagi tu kan. If you understand that, you don't have to come to my class. No problem. Tak ada masalah. If you understand, you don't have to come to my class. So you can use your time to do many amal soleh. Bukan main game. Okay. So only those near the mid gap are effective recombination centers. The trap and remember we talk about sebelum ni, saya tak tahu saya explain ke tak on the defects. This is the conduction band, valence band. So if you have two semiconductor material with the same band gap, one have a trap, energy level trap in the middle, and the other one like this, slightly at the bottom. Okay, so this is A, semiconductor A, this semiconductor B. Which one will have a higher dark current, higher current? A or B? Ni biasa soalan final exam juga. Ada jawapan? Kalau tak ada jawapan, saya biarkan kosong. Pandai-pandai awak jawab sendiri. Senyap lah. Okay, tak apa. Try to find out.
The question again, madam.
So between A and B, which one will give a higher dark current? Dark current, it means that it's in the dark and the excitation is only due to thermal. That's what dark means. It's in the dark. So this is important, dark current ni especially for photodiode. The group yang buat photodiode tu, photodetector tu. Photodetector, photodiode is the same thing. Jangan confuse photodetector, photodiode, same thing. And they use the term dark current, DARK, dark current. Okay, dark, in the dark. It means that we do the experiment or we do the measurement in the dark. There's no light. Therefore, the source of excitation can be only due to thermal. It cannot be, but light can also excite. So between A and B, which one will give you a higher current? Kalau saya tak pakai dark, saya pakai higher current lah. Okay, you think of the answer, tell me next class. And if you don't remind me the answer, I will forget about it, then I'll tak jawab dalam final exam. So up to you. If you want the answer, remind me, give me the answer next class, I will verify whether it's right or wrong. Okay. Kalau awak tak ingat, saya pun lupa. Sadaqallahul azim. So that's it lah. Bila nanti pandai-pandai lah. Sebab kalau saya tak cerita pun jawapan, you should be able to think. So that's why things that I ask you in class is something that you can think. Things that I know that you cannot think, not possible because tak cukup ilmu, I will not ask you to think. But this one you can think. Boleh fikir. Okay. Career lifetime ni. Tak payahlah kot. Okay, light absorption and transmittance ni is important for photodetector. So those who are explaining the photodetector, make sure you talk about light absorption and transmittance. Okay, part of the theory. Sebab mungkin ada soalan dalam final exam. It's also an interesting graph. This is a graph of, so maybe you can explain in terms of this graph. This graph is the absorption coefficient versus wavelength. Absorption coefficient of the semiconductor versus wavelength. So for different semiconductor material, so germanium, dia macam ni. So what does it mean? So thermal emission ni kita tak cover. Kalau buat master research dalam bidang ni mungkin saya cover. Tapi since none of you, kalau saya cover dengan student saya je lah. Student orang lain tak pakai pun benda ni. So Fraggle pun tak cover. Tunneling pun tak cover. You are lucky you don't have this assignment too. It's difficult. Normally I give to master student level. Tapi master kali ni pun you are lucky I will not give this question. Okay, I think that's all for today. So next class we'll talk about BJT lah. So you already read, jangan lupa, don't delete your memory on BJT. Al-ilmu hahuna. Ilmu tu di dada. So jangan delete lah. Ilmu tu nur. So jangan delete ilmu on your BJT. Well, let's have a discussion on it next class insyaAllah. Okay, any question for today? Make sure, try to get the answer for that. And try to read more of the general knowledge. Okay, I think that's it for today. Let's have sebab next memang betul-betul dah masuk BJT, so all the basics are done, habis. So next cuma ada satu, saya tak tahu lah. Saya dah pernah cover tak kalau macam depletion region, effect of carrier concentration to depletion region. Ada tak saya cerita? Kalau tu saya suka tanya juga exam. Saya dah beritahu semua jawapan exam. So awak tak jawab juga tak tahulah. Tak jawab, fail lah awak. So that's a PN junction, right? So there's another thing that I want you to think. If you don't tell me the answer, that's it lah. Sadaqallahul azim juga. Tak jawab. Tapi still awak boleh fikir sepatutnya. Ni PN junction A. This is PN junction B.
We cannot see anything. Right?
Allahu Akbar. Thank you. Aduh lah, kenapa tak cakap bawah lah ni. Lupa. Okay. Nampak dah? Can you see? Yes. So you have PN junction A, PN junction B. This is P, this is N, this is P, this is N. So one having a concentration of okay, so katalah P ni concentration dia 1 × 10⁻23 per centimeter cube. N ni pun 1 times 10 to power of 23 per centimeter cube. And B ni 1 times 10 to power of 23 per centimeter cube for P. N ni 1 times 10 to power of 21 per centimeter cube. Okay, can you see the difference? Ni 23, 23, 23, 21. So difference in the carrier concentration. Draw me the depletion region. Draw me the depletion region. How, macam mana dia size of the relative depletion region here and here. Okay, try to think about that. And tell me the answer next class. If you don't tell, kita memang skip lah tu masuk BJT. And this have to do with the, you need to understand this, you need to understand the space charge region. How much, how many, in order for recombination to occur, dia kena satu electron dengan satu hole. Okay, one electron and one hole. So now you can see the concentration of the hole is not the same as the concentration of electron for B. And then in the end, how does the depletion region looks like? Okay. Alright, so I think that's all. Nanti you fikirlah, and then boleh tanya saya kalau ingat, kalau tak ingat, that's it. Kita go BJT. Yang biasa student tak jawab soalan ni. Itu final. Saya pun tak tahu, kadang saya cerita dalam kelas lah, berbuih mulut saya cerita dalam kelas. Tapi tak tahu kalau recording ni mungkin awak akan ingat kot. Kalau dalam kelas biasa tu, cerita tak, jangan buat, jangan. Oh, dalam exam ada. Kata, ya Allah. Okay. So, alright, let's have a brother. Siapa yang tak pernah recite doa ni, tolong baca doa. Kita tutup kelas. Kita boleh rehat lah. Siapa yang, you know who you are? Ke semua brother dah baca? Kalau semua dah brother baca.
Me, madam.
Okay, silakan.
Auzubillahi Bismillahirrahmanirrahim. Alhamdulillahirabbil Wassalatu wassalamu ala asyrafil anbiya wa mursalin wa ala alihi washabihi ajmain.
Amin.
Allahumma ahyina bil iman wa amitna bil iman wa adkhilna jannata ma'al iman. Allahumma ighfir lana dzunubana wa liwalidayna warhamhuma kama rabbayana shaghira.
Amin.
Allahumma khtim lana bi husnil khatimah wa la takhtim alaina bi su'il khatimah.
Amin.
Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala
Sayyidina Muhammad wa ala alihi wa sahbihi wa sallam. Walhamdulillahirabbil alamin.
Sayyidina Muhammad wa ala alihi wa sallam.
Okay. Thank you, Azibuddin. Okay, thank you. Let's close the class with tasbih kifarah and salam. Subhanakallahumma bihamdika ashhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'ashr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. Everybody can leave except for Amirul Faris. Tunggu. And the rest of you, please leave.
Thank you, madam.
Welcome.